Hello, I'm Dr. Konstantinos Barmpis, and today I will be presenting the work done on CrossFLOW, a framework we have developed at the University of York for polyglot and distributed software repository mining. CrossFLOW is a platform for the creation and execution of heterogeneous and incremental analysis workflows. This is done through the use of graphical or textual editors that are used to create such workflows. Then, code generation techniques are used to automate the creation of the orchestration and other boilerplate code required for these workflows to be executed in a parallel or distributed manner. Workflow execution can be monitored through a web UI or using the various monitoring queues available while CrossFLOW is running. This work has been developed at the University of York as part of the Horizon 2020 CrossMiner project. Let's take a look at the architecture of CrossFLOW. On the left, we can see that the workflow is created through a domain model. This model conforms to the CrossFLOW meta model and is created through either graphical or textual editors by the domain expert. When the domain expert has created this model, code generators are used in order to create the boilerplate code required for this workflow to be amenable to parallel and distributed execution. After this is done, the developer can then implement the code they require to be executed for each of the workflow tasks. Finally, the code will be packaged and ready to be executed in one or more nodes in a distributed fashion. The domain model itself can be seen here, and we will now go through its important elements. A workflow is made up of a collection of tasks. A task defines a process in the workflow that is going to be executed, and these processes are independent of one another. Such tasks can be defined as running only on the master, and also as producing more than one output for a single input. These tasks are also written in a specific programming language. Tasks are linked together through streams. A stream is either a queue, whereby a single output element will be consumed only once, or a topic, whereby each output will be consumed by all parallel and distributed instances of a task, as it is being broadcast to all of them. Streams are strongly typed with the ability to define any type that is able to be serialized and sent through the messaging middleware used, such as most primitive and serializable types in programming languages like Java and Python. If we look back at tasks, there are quite a few specializations offered. A source is a task that has no input and is commonly used at the beginning of a workflow to perform a one-off sending of data to then be used by other tasks. Similarly, a sink is a task that has no output and is commonly used at the end of a workflow in order to gather all of the output data together. These two types of tasks will only run on the master, so we'll have access to all of the data to be sent or received, respectively. Other tasks include opinionated tasks that are able to reject elements based on custom code executed upon receiving each element. Today, we will look at the following running example, which is also used in the paper. In this example, we have a technology source that is producing a set of technologies to be used by the workflow. These technologies include a name, a keyword, and an extension. For example, the technology Java would have the extension .java and the keyword class, which would commonly define a file that contains source Java code. These technologies are passed to the CodeSearcher task. This CodeSearcher will use this input and search GitHub for appropriate files of this technology. It will then send the repository URL these files are found in to the repository's queue. The repository's queue is consumed by the search dispatcher task. This is a task that will run only on the master and gets all of these repositories and filters out duplicates, ensuring that appropriate searches are only performed once. These searches will then be run in the repository searcher task that will clone the appropriate repository. After it is done cloning the repository, it will perform a file search on this clone to find out how many files of technologies of interest are found in it, and will send this count to the search results queue. Finally, the sync will collect all of these results and store them so that they can be visualized and retained. Here, we see how this running example can be created using a graphical editor. In this case, the editor is embedded inside the Eclipse IDE, and we can see, on the left-hand side, the complete diagram for this running example created using this editor. In the center, we can see the palette that has the various options that were in the domain language, such as the different types of tasks, streams, and data types, as well as connections that we can create between these elements. These arrows here represent these connections. On the right-hand side, we can see that for a selected element in this graphical editor, in this case, the repository search ditch pasture, we have the various properties that we saw in our domain language. In this case, this is a task element, so has its input and output streams, in this case the repositories and repository searches streams, whether it is going to run only on the master, or whether it's going to produce more than one output for each input. Let us now look at how CrossFlow executes a workflow, such as the one defined in this running example. The current state of the art contains various distributed execution engines, like Apache Spark and Apache Flink. Such tools did not seem to be able to cover several of our requirements, like offering the ability for specific jobs to be channeled to specific workers, or for workers themselves to be able to reject jobs they do not wish to process. Usually, such systems treat each worker as having similar capabilities to its peers. As such, we decided to work on the messaging middleware as the basis for our system, in order to provide us with the ability to control how the system manages concerns like these. We are using the Java Messaging Service API, and more specifically, the Apache ActiveMQ tool. It provides the two basic structures we saw in the domain model, queues and topics, and offers a broker set up on one or more nodes, and will expose these streams over TCP, allowing for workers to connect whenever they are available. CrossFlow uses code generation to create most of the boilerplate code needed for a workflow to be ready to execute in a parallel and distributed fashion. This offers two main advantages. The first is that the code will be strongly typed, as this is known from the domain model, aiding in the implementation of the various tasks. And the second is that the developers will only have to write the logic of each task, focusing on implementing their core analysis logic and not having to worry about orchestration or execution code. CrossFlow will then be able to run a parallel and distributed execution of this workflow, and also offers various metadata and logging queues that can be used for monitoring this execution. For example, finding out how many current messages are there in the various queues of the workflow, or which tasks are processing and which are currently idle. CrossFlow also importantly offers the ability to implement each task in its appropriate programming language. For example, a task that has powerful libraries in Python can be written in Python, whereas a task with good Java libraries can be written in Java, all for the same workflow. In the running example, we saw one of the tasks, CodeSearcher, as being defined both Java and Python, whereas the repository searcher task was defined in Java. This means that for the CodeSearcher task, one of the workers can be running in Python, executing this task, and one of the workers can be running in Java, executing this task, as well as the repository searcher task. Let us look at some example code for these tasks. In this case, the technology source task. Here, we can see that there is a produce method, which will run once at the start of a workflow, only on the master node. This method will read from an input file, and for each line in that file, will produce a technology tuple and send it to the technologies queue. Next, let's look at a task, the repository searcher task. Repository searcher has the consume repository searches method. Without going into the implementation in detail, the method will return an analysis result object to be sent to the appropriate queue, and consequently to the sink for collection. Notice, in the repository searcher task, there is an arrow going back to the repository searches queue. This is because this task is an opinionated task and can reject jobs based on the logic written in its accept input method. When such a job is rejected, it is returned back to the originating queue, in this case, the repository searches queue, so it can be resent to a different node to be analyzed. Finally, we can see an example of a task implemented in Python, the CodeSearcher task. Similarly, the specifics of the code do not matter, but we can see that the task reads technology elements, consuming them from the technologies queue, and sends repository elements to the repositories queue. We have performed a quantitative evaluation of the scalability of CrossFlow using a more complex scenario, described in detail in the paper. In short, this scenario aims at offering metrics for open source software projects and using them to calculate an estimate for the effort required for developing new projects. Similarly to the running example, it consists of both Java and Python tasks. This evaluation has been performed on 8 different setups run on the cloud. And for each setup, we record the execution time and memory consumption of the code. We provide a detailed analysis for these results in the paper, as well as how we believe they offer insights into the scalability of the system. Overall, the results obtained seem to scale both with parallel instances running on multi-core systems, as well as distributing the workload on multiple worker nodes. Here, we see a graph of the execution time for 5 of the deployment setups. We can see that as we increase the resources available, the memory, number of cores, and number of deployment nodes, CrossFlow executes the workflow, taking progressively lower amounts of time. In summary, today we looked at CrossFlow, a tool for the creation, execution, and monitoring of heterogeneous, distributed analysis workflows. We presented the architecture of the system, showing how its various components fit together. We then presented the domain language, using the concept of a workflow made up of tasks and streams linking those tasks together. CrossFlow offers a graphical editor for creating such workflows, and also has a textual editor omitted due to time constraints. Code generation is used to provide the boilerplate code required, allowing the developers to focus on implementing their core analysis logic without having to worry about orchestration or execution code. The source code for this tool can be found at the URL shown here, and the tool is continuing to be developed actively by the partners at the University of York. Thank you for your time. I would be happy to answer any questions you may now have.